Okay, so let's look at a worked example for a common base amplifier. I'm going to follow the theory from video part 1. So we've got a BJT transistor, NPN. So we've connected the base to 0 volts there. We've got the emitter. This is the, we'll call this the RE resistor, typically RC resistor, because we've got the collector, the emitter, and the base there. Bias this minus 10 volts. This one 15 volts. And what we'll see with the common base amp, we'll take the output from the collector, value 10U. Just going to connect it to a load, RL, 2K5, 5K, and we're going to put an input signal in. I'm going to put it into this emitter point here via a cap. So I'll call this my voltage source, AC, 0 volts, 100 microfarad. Right, so from the previous video we saw that the effective input impedance of this amplifier is this RE, this big RE resistor, in parallel with little RE1, which is the base emitter impedance. So just put little RE1 there, so we can write Z in equals RE in parallel with little RE1. So on this particular example, we can see we've got this connected to minus 10 volts. So, and this is 0 volts. So we're going to get approximately 0.65 volt drop across this base emitter junction, which means we're going to have approximately 9.35 volts across this big RE resistor, which will then, because we know this resistor 9K1, we can establish what the emitter current will be, i.e. Q. Now the reason being is we know that RE1 is 26 millivolts divided by the IEQ. So IEQ is approximately equal to 9.35 divided by 9K1, which is approximately 1.03 milliamps. So that's ohms. Okay, so based upon that we can establish what our input impedance will be. So once we found the IEQ, we can find little RE1 if you pop that into your calculators. So 26 millivolts divided by 1.03, we get little RE1 approximately equal to 25.3 ohms. So knowing that, we can establish what Z in is. And if we take 9K1 in parallel with 25.3, then we get approximately 24.96 ohms, call it 25 ohms. So we've got an input impedance that this source sees of approximately 25 ohms, which is kind of what we'd expect. It's a common base amp. We're hoping to see very low input impedance. which is great. And one thing to bear in mind, because it is low input impedance, we don't want this input signal to be, in super volts range. Otherwise, it's going to draw lots and lots of current, and we can get into issues. So just bear that in mind in your designs. The current gain of this particular amplifier is going to be, works out approximately equal to 1. Again, look at the previous video to see how I established this. But the voltage gain, AV, AC voltage gain, what we can say is there's a few kind of assumptions that we can make here. We can say that this Zin is going to be more in line with provided the big RE resistor is much bigger than the little RE resistor, then this Zin is going to tend towards this little RE1 resistor. We can see here that RE1 is 25.3, Zin is 24.96, which is much, we could say it's approximately the same. So voltage gain, we've got current times the impedance output divided by the input current times by the impedance input. So we can start to think about this in terms of the output impedance. If IEQ and ICQ are approximately the same, then we can, this would be times ICQ, so we can cancel that with the IEQ that's on the bottom. And we can also say that rather than putting RE in parallel with RE1 here, we can just say, well, this is RE1, and this gives us our voltage gain equation. And if we tap in those values, then we'll see we'll get 5k divided by 25.3 and 197.63. Yeah, quite a lot of voltage gain. Very low input impedance, high voltage gain. Now, one thing to bear in mind with this is the moment I place this load resistor on the output, then the IEQ, what we'll see is RC will become paralleled with the RL. So really, a more complete equation will be RC in parallel with RL over RE1. And if you tap those values into your calculators, then we will see that our total on the top comes out at around 1667 ohms, and divided by RE1, and what we'll get is approximately voltage gain of about 65.9. So, as with any amplifier, we have to consider the load that we're driving, and it will impact the overall voltage gain of this arrangement. Let's have a check. So this 1.03, we're saying that's the quiescent current. We're looking at voltage gain, so 65.9. Okay, so let's have a little look-see at that on LTSpice. So we've got -10 here, so that's the bias. 5k, 2k5, got our voltage source. Just going to check this. It's got no series impedance, and it's going to have a peak voltage of 1 millivolt. So let's just run this. Look at the input. That's our 1 milli peak to peak. And what we're looking for, hopefully, is something around 60 millivolts, 65 millivolt peak on this output. So let's have a look. And sure enough, that's what we have. So that's fantastic. Now it's never going to be exact. There's a bit of asymmetry. See, as the AC signal oscillates, this causes slight variation in the VBE because there's an exponential relationship between IC and VBE. Therefore, this is the reason why we get some asymmetrical distortion. The other thing we want to check, the bias current. So let me just measure this. Let's just disconnect that source. Run it again. Well, look at this. I've got a bias current 1.03, which is what we calculated it to be, so that's cool. Let's disconnect let's keep that connected for now. Let's just have a little look at the input impedance. So I'll just run this. So this is with input impedance we're assuming the source here has an input impedance of 0 ohms. Well, that's hardly ever the case, but if we make this input impedance match the input impedance of the amplifier, then what we should see is half this this amplitude, because we get half dropped across essentially it's a potential divider between the source and the amplifier itself. So what did we calculate that to be? We said Z in approximately 25 ohms. So let's just make this 25 and see what we get now. Yeah, it's looking about right. 30 millivolts, approximately half. That's all good. Obviously, if I disconnect this, disconnect the load, run it again. Let's close that down. Yeah, we get a lot bigger gain. That's what we'd expect. So what is the total gain? Let's just knock that down to 0 again. So we've got no source impedance and no load. And we're seeing, what's that? 165, 165. I think we calculated it to be 197. Not going to be exact because of the model of the transistor, but we're there or thereabouts. That's the beauty of analog electronics, I guess. We're about sort of certain approximations, which is all good. So in the previous video I mentioned, we can bias this negatively, but we could also put a potential divider bias to this emitter point here. So I'll just show you what I mean by that. So here we've got essentially an equivalent where I've got a positive. I don't need the negative supply rail. So let's just check this one. So 10, 0, 0. Okay, so that's with a load. 0. Okay, so settings are comparable. Let's just see if what these look like. So that's our input. That's our output, which is what we previously got. And let's have a look at the output of this second amp. Yep. Again, comparable, I would say. Still 59, 52. Yeah, there or thereabouts. Slightly less voltage gain with this version, but let's have a look. So V out 1, look at the distortion of the amp. So Spice error log. So this is the THD looking at V out 1, and we get a THD 0.88%. Not cracking, but not bad, I suppose. So let's just change this analysis. And look at this amp now. Let's just run it again. Ooh. 0.71. We've improved it, but obviously we are lowering the gain a little bit, but hey ho, that's okay. So hopefully you can understand a little bit more about common base amplifiers and the configurations, and how we've been able to add some different sort of forward bias arrangement across this junction to get the transistor into the active region. So just to further an explanation on the asymmetry that we saw previously, if we look at the input signal, so we've got 2 millivolt peak to peak. So I've changed the input impedance to 0. Let's just run that for this particular amplifier. So we're doing an analysis. So this is what we saw previously. So 123 millivolts peak to peak. But we can see we've got somewhat of some asymmetry here. So if we match, we said that the amplifier had an input impedance of 25 ohms, so I'm going to make the source 25 ohms. This is effectively going to halve the input signal going into the amplifier. Now the previous THD we saw was 0.88, so if we run this again, we'll see that we've got actually an improvement in the symmetry of this output signal, but we've got a THD now of 0.24. If we reduce this even further, keep the input impedance the same, or sorry, source impedance the same, but THD has dropped again massively, because we're essentially, we've got, if we think about small signal analysis, we've got this VBE, we've got an AC signal coming in which is superimposed on the DC operating point. So this is going to cause variation, and this variation, as I mentioned earlier, the relationship between VBE and IC is exponential. So if we keep the variations small, then we can essentially approximate that there's going to be a linear relationship between the IC and VBE. However, as we make the variations larger, then we see that the relationship's exponential, so we see this more distortion.